Storage retrieval. In Chapter 2, we discuss data models and query languages, i.e. the format in which the application developer gives the database your data and the mechanism by which you can ask for it again later. This chapter, we discuss the same from the database point of view. How can we store, how we can store data that we're given, and how can we find it again when we're asked for it. In particular, there's a big difference between storage engines that are optimized for transactional workloads and those that are optimized for analytics. We will explore that distinction later in transaction processing or analytics and in column-oriented storage. We'll discuss a family of storage engine that is optimized for analytics. So there's two ways for us to query and store data, analytics and transactional database storage engine. We will discuss both in a separate part. So basically, it may sound abstract, but since we're able to define the query language and describe it, now we will describe how we can actually store it and query it given the restrictions of our current computers such as memory, CPU, and disk. However, first we'll start this chapter by talking about storage engines that are used in the kinds of database that you're probably familiar with. That you're probably familiar with traditional relational databases and also most so-called NoSQL databases. We'll examine two families of storage engines, log-structured storage engines and page-oriented storage engine such as B-trees. So we will discuss first the storage engine for relational database, and next is the storage engine for document databases. But before that, we need to distinguish this log-structured storage engine and page-oriented storage engine. And to distinguish that, we need to know what do we mean by log. Data structures that power your database. Consider the world simply as database, implemented as two bash functions. So a bash function is a good way to explain this because this is where the first or the log structure came. So this is actually how we understand log. So remember, this database also came from Unix operating system, which primitives create compounds that allow us to create the shell. So here we have two bash functions. These two functions implement a key value store. You can call db underscore set key value, which will store key and value in database. The key and value can be almost anything you like. For example, the value could be JSON document. So you can then call db underscore get key, which look up the most recent value associated with that particular key and returns it. Like db set 12345 6 and then code name London, etc. And then db set 42 name San Francisco and db underscore get. You have name colon San Francisco, comma attractions colon Golden Gate Bridge. The underlying storage format is very simple. A text file where each line contains a key value pair separated by a comma, roughly like a CSV file, ignoring escaping issues. Every call to db underscore set appends to the end of the file. So if you update a key several times, the old versions of the values are not overwritten. You need to look at the last occurrence of a key in a file to find the latest value. Hence the tail -n in db underscore get. Our db underscore set function actually has pretty good performance for something that is so simple, because appending to a file is generally very efficient. Similar to what DB underscore set does, many databases internally use a log, which is an append only data file. So the storage format for this is not JSON. It's a CSV. It's a comma separated values. Every call to DB underscore set appends to end of that CSV file. So if you update a key several times, the older versions of the value are not overwritten. So it's not being updated as it is where it was. You need to look at the last occurrence of a key in a file to find the latest value, hence tail dash n1 in db underscore get. Our db underscore set function actually has a pretty good performance for something that is so simple, because appending to a file is generally very efficient. Similarly to what db underscore set does, many databases internally use a log, which is an append-only data file. Real databases have more issues to deal with, such as concurrency control, reclaiming disk space so that log doesn't grow forever, and handling error and partially written records. But the basic principle is the same. Logs are incredibly useful, and we will encounter them several times in the rest of this book. So that is the first storage engine or type of storage engine that we have. So this log data structure, which we append something at the end of the file, is actually very useful. The only difference with the real storage engine with this is the actual concurrency control of the OS, the reclaiming of disk space, and how it handles corrupted data, which, as you know, we encounter in real world, especially for distributed systems, where a lot of uh, concurrent users are sending requests to different data center. The word log is often used to refer to application logs, where an application output text that describes what's happening. In this book, log is used in a more general sense, an append-only sequence of records. It doesn't have to be human readable. It might be binary and intended only for programs to read. So a log is actually an append-only sequence of records. So it's used to describe an append-only sequence of records in those computer structures such as OS, RAM, and disk. It doesn't have to be human readable. It might be binary and intended only for other programs to read. On the other hand, our db underscore get function has terrible performance if you have a large number of records in your database. Every time you want to look up a key, db underscore get has to scan the entire database file from beginning to end, looking for occurrences of the key. In algorithmic terms, the cost of lookup is ON. If you double the number of records in your database, a lookup takes twice as long. In order to efficiently find the value for a particular key in the database, we need a different data structure. So because these are too simplistic, with you just only using the basic commands of Unix, we need another way to search for a particular value with a key, in this key value storage in CSV. So we need a new data structure, an index. In this chapter, we will look at a range of indexing structures and see how they compare. The general idea behind them is to keep some additional metadata on the side, which act as a signpost and helps you to locate the data you want. If you want to search the same data in several different ways, you may need several different indexes on different parts of the data. So this index is essentially another way for us to query it so that it will be fast. But as we will later see, there is actually a trade-offs in write and reading because we would usually read, but some application actually is write heavy. So this structure, maybe the log append without any modification to its query may be appropriate. But for most application that is read heavy, we need to tweak this data structure or we need to index it better to be able to search it faster. An index is an additional structure that is derived from the primary data. Many databases allow you to add and remove indexes, and this doesn't affect the content of the database. It only affects the performance of queries. Maintaining additional structures incurs overhead, especially on writes. For writes, it's hard to beat the performance of simply appending to a file because that's the simplest possible write operation. So because the write is the simplest and the fastest in this log uh, storage structure, it's hard to beat the big O performance because you just need to append it at the end of the file. Any kind of index usually slows down writes because the index also needs to be updated every time data is written. So if we create or if we tweak how we search it by also creating an index, we also slow down the writes, which is the most the file which is its length. This is an important trade-off in storage systems. Well-chosen index speed up read queries, but every index slow down writes. For this reason, databases don't usually index everything by default, but require you, the application developer or database administrator, to choose indexes manually using your knowledge of the application's typical query patterns. Hash index. So let's start with indexes for key value data. This is not the only kind of data you can index, but it's very common and it's a useful building block for more complex indexes. Key value stores are quite similar to the dictionary type that you can find in most programming language and which is usually implemented as a hash map, hash table. So let's start with indexing a key value data. Note in data structures and algorithm video, in the previous video, this is not the only data structure that we can index, but it's a useful building block for other indexes to be able to understand how to index other data structure. Key value stores are quite similar to the dictionary type that you can find in most programming languages, and which is usually implemented as a hash map, hash table. So a key value store data structure is similar to a dictionary. In Python, you would see this as a dictionary, which is usually implemented as a hash map or hash table. So this key value, or it's actually a hash table. I mean, we discussed this as a hash table in data structure video. Since we already have hash maps for our in-memory data structures, why not use them to index our data on disk? Let's say our data storage consists of only appending to a file, as in the preceding example, then the simplest possible indexing strategy is this. Keep an in-memory hash map where every key is mapped to a byte offset in the data file, the location at which the value can be found, as illustrated in figure 3.1. So you really need to have an understanding of RAM and disk, since on our previous and also on OS. Since in our previous example, we already have log, and those log has a basic RAM and disk, right? Because that's the common requirements for a computer to work, and you have an OS on top of it. Now, for this indexing strategy, since you already have that memory, you would use that memory to implement, and also as well the programming language to implement that data structure in memory to and use the offsite byte in the disk to to move use the offsite byte in the disk to and use the offsite byte in the disk to 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 find the value. Since you have a key and value, since you're indexing a key and value, you would put the key in the memory. So here's the example. Byte offset 0 here and byte offset 64 here. Here's the actual disk data. Whenever you append a new key value pair to the file, you also update the hash map to reflect the offset of the data you just wrote. So whenever you will add a new key value to the actual disk, you also update the in-memory to reflect offset of the data you just wrote. This works both for inserting new keys and for updating existing keys. So it works for writing a new key and updating the existing keys. When you want to look up a value, use the hash map to find the offset in the data file. Seek to that location and read the value. So the algorithm for you to be able to look a value in the disk is to use the hash map or the hash table you have created in your programming language, such as this. You would use that 64 to find the offset in the data file. Seek to that location and read the value. Figure 3.1, storing a log key value pairs in a CSV-like format. Index with an in-memory hash map. This may sound simplistic, but it's a viable approach. In fact, this is essentially what Bitcask, the default storage engine in React, does. So Bitcask is a known storage engine. It's known to provide a lot of storage engine and database services. So it's being used in the industry. And this type of hash index with the log structure that we have discussed is actually what they use. It's very simple. Bitcast offers high performance reads and writes, subject to the requirements that all keys fits in the available RAM, since the hash map is completely in memory. So this structure provides a fast read and write, providing that your data or the key value file fit in memory, because remember this is all are in memory. The values can use more space than there is available memory. So the value, since it's stored in disk, it could use more space than the keys, because keys are what's stored in memory, since they can be loaded from disk with just one disk. 6. If that part of the file is already in the file system cache, a read doesn't require any disk I/O at all. If it's already in the file system cache or in the TLB cache, remember the TLB with the page disk of the OS. Once it accesses it, it puts that on the most recent access, so therefore it will save it. So if it's already in there in that cache, RD doesn't require any disk IO at all. That's the reason why you have fast read and write. A storage engine like Beatcast is well suited to situations where the value for each key is updated frequently. For example, the key might be the URL of a cat video and the value might be the number of times it has been played, incremented every time someone hits the play button. In this kind of workload, there are a lot of writes, but there are too many distinct keys. You have a large number of writes per key, but it's feasible to keep all keys in memory.